What's going on, Algebros? Mr. C here to talk about the domain of a logarithmic function. First and foremost, I want to lead off right off the bat with saying that the domain of the logarithmic function is generally not going to be all real numbers. And to give you some explanation as to why that is, I have a couple of toy problems here. These come courtesy of page 6 of the section 6.4 note packet. I want us to try and kind of revisit the concept of what the log notation stands for. For instance, when we're reading this statement here, this is saying that log base 2 of 0 is equal to something. Conceptually, you're thinking to yourself, what power of 2 would give you 0? Now, if you're struggling with that, don't feel bad. If you wanted to, you could even rewrite this using a log loop and saying 2 to the question mark is equal to 0. So you want to think, all right, well, what power of 2 would generate the number 0 for us? And spoiler alert here, there actually isn't a power of 2 that's going to turn it into 0. If you're thinking use this, or the question mark could be the number 0 itself, I got news for you. 2 to the 0 is not equal to 0, it's actually equal to 1. Alright, so this actually doesn't really have a solution to it. I'm actually going to write it out this way. I'm going to say DNE. That's notation for does not exist. So the power of 2 that gives you 0 doesn't exist. There isn't one. Alright, let's look at log base 2 of negative 4. Again, the concept is what power of 2 gives you negative 4. If you try to rewrite this using a log loop, it becomes 2 to the question mark equals negative 4. Alright, so now you ask yourself, okay, well 2 to the what gives me negative 4, and this is another situation where the answer does not exist. If you think raising 2 to the negative 2 would give you negative 4, that actually doesn't work because 2 to the negative 2 is 1 over 4. In fact, there's no power of 2 that will give you an output that's negative. To see why this might be, what we could do is do a quick sketch of the function 2 to the power of x. 2 to the power of x, since the base is larger than 1, is going to start out along the negative part of the x-axis, go through a y-intercept of 0, 1, and then just explode off to positive infinity. And that's a quick sketch of 2 to the x. You may want to recall that all exponential function graphs come equipped with a horizontal asymptote, and 2 to the x is no exception. There's actually a horizontal asymptote along the x-axis, and the equation for that would be y equals 0. So in looking at the graph, notice that the graph of 2 to the x is entirely above the x-axis, meaning that there aren't going to be any y values on this graph that are negative, nor are there going to be any y values that come out to be 0. Alright, keep in mind, as we discussed in class, if we were to trace this graph going right to left, this part of the graph doesn't necessarily, or actually doesn't at all, intersect or cross the x-axis. So these y values just continue to shrivel down and get closer and closer to 0, but not necessarily reach the value 0 itself. So from a graphical perspective, we can see that log base 2 of 0 doesn't exist, nor does log base 2 of negative 4. Overall, here's a rule that you want to keep in mind regarding logarithms. You can't take the log of a negative number, and you can't take the log of 0, because none of that is going to exist. So that's a nice segue into these last two examples for section 6.4, as well as what's stated in the box here. It says to find the domain of any logarithmic function, here's what you do. You take the argument, or the inside part of the log function, and you force it to be greater than 0. This is really just representative of the fact that since we can't take the log of 0 nor a negative number, then the only numbers that are allowed inside the log are positive. So this kind of gives us an algebraic strategy for figuring out, what x values can we plug into any random log function. Alright, so let me go ahead and illustrate this to you. Our first example is f of x equals log. Notice the base isn't written, so we assume it's a 10. And in the argument, we have the expression x plus 5. So according to everything above, all those remarks, and what's in the box, x plus 5 is only allowed to come out to be a positive number. So for that reason, I'm going to take it out of the log function and set it greater than 0. And what you do from here is just solve a basic linear inequality, move the 5 over, and we see that the only values of x that we're allowed to plug into this log function are those that are greater than -5. Alright, we are requesting interval notation, so the interval notation for that would be parentheses -5, comma, infinity. So if you think about it, one value of x that's not part of this interval notation is something like -10. If you were to plug -10 in for x, we'd be taking the log of -10 plus 5, which breaks down to -5. So the log of -5, there is no power of 10 that would give you -5. So that's just a quick random example of x, just illustrating why we can't use anything less than -5. And notice the parenthesis on -5, that means we're not going to include -5, because if you plug -5 into x, we wind up taking the log of 0, which doesn't exist. So any value of x that's greater than -5 is a legit value of x to plug in. All right, even something like 0. All right, if you did the log of 0 plus 5, that's the log of 5, and we'd be able to, perhaps using a calculator, figure out what power of 10 gives us 5. All right, one more example. In part B here we have the natural log, so that's log base e in disguise, and in the argument is x over x plus 3. So again, by virtue of the remarks from the above part, we want to make sure that whatever x values we plug into this argument force us to take the natural log of something that's positive. So algebraically, what that means is let's just go ahead and take x over x plus 3 and force it to be greater than 0. So the technique for solving for x here is a little bit different, because technically we're looking at a rational inequality. And what you don't want to do is multiply both sides by x plus 3. That would be okay if this were an equal sign, but since it's a greater than sign, it's an inequality, and we have a different technique for helping us to solve a rational inequality. So let me go ahead and give you some reminders on how you would do that. What you'd want to do is make sure that this fraction right here is a single fraction, and both the top and bottom are fully factored. And we're kind of in a nice situation because there's no factoring x and there's no factoring x plus 3. So what you do from there is you find both the zeros of this expression and the vertical asymptotes if it has any. I'm going to draw up a quick number line. The 0 of this rational function actually comes from setting x equal to 0. Alright, so you may recall that to find the zeros of a rational function, we set the numerator equal to 0. And setting x equal to 0 gives us 0. So I'm going to put that on the number line. The vertical asymptote for this rational expression would be -3, because if you plug -3 into the denominator, you get division by 0. So -3 should also be going on our number line. And what I'm going to do is quickly put an x on top of that -3. And just note that -3 is a vertical asymptote. And basically this just helps us to avoid including -3 as part of our final answer. Then what you want to do from here is pick and choose some test points. So we'll start with a value that's less than -3, maybe -4. Alright. What we're going to do is consider the rational expression here as our f of x. Or if you want to use g of x, since we're already using f of x for the log function, that's fine. But if we plug -4 as like a test point into our function g, or the rational expression, we'd have -4 over -4 plus 3 is -1. That gives us a positive output, namely positive 4. So according to our theory of inequalities, any value of x that's less than -3 will make this expression positive. Alright, if you want to pick a value between -3 and 0, say -1, do g of -1, that would give us -1 on top of -1 plus 3 is positive 2. So that gives us a negative output of -1/2. So according to our theory of inequalities, any x value between -3 and 0 is going to make the expression x over x plus 3 negative. All right, let's do another test point. This time a value to the right of 0, maybe positive 1. G of 1 would give us positive 1/4. So again, just based on our theory, any values of x that are greater than 0 will force the rational expression to be positive. Now keep in mind, because we want the argument of the natural log here to be positive, as indicated by the inequality symbol, we're going to want to keep the parts of the number line that are marked as positive. So we're about ready to draft up our final answer. We're going to do some interval notation here. Here's the domain of f of x equals the natural log of x over x plus 3. Parentheses negative infinity, comma negative 3, parentheses, union, parentheses 0, comma infinity. And that's a wrap. Thanks for watching.